Good evening, kiddos. It's about 11:15, and I'm really tired, so I have absolutely no clue how this is going to go. Hopefully, it'll make sense, though. So, first things first, we need to look at what, Cleo? Come here. That's Cleo. She wants to say hi to everybody. So, first things first, we need to talk about make sure we're all on the same page with the same vocab. What, Cleo? So here we have a radical. The entire thing together will be called the radical. And so we have the index, and that is the degree of the radical. The same way that exponents have x squared, x cubed, x to the fourth. We can have the third root, the fourth root, the fifth root, and so on and so forth. And that's determined by the index. The actual little check mark looking thing, that is the radical. It's the radical sign. The term or number or variable or whatever which is inside the radical is called the radicand. And then the number that is outside of it is called the coefficient. So those are the terms we're going to be using. So first let's talk about adding and subtracting. So when we're adding and subtracting, we need to have the same index, the same radicand. So if we have the same index and the same radicand, then what we can do is we can add or subtract them. And to do this, what we do is we add or subtract the coefficient while leaving the radical alone. Okay, so for example, if we have the square root of 2 plus the square root of 2, square root of 2 plus the square root of 2, so there we have the exact same index, 2. It's important to remember that if we don't have a index, if it's not there, then it's a 2. So we have the same radicand, and we have the same index. So we can add them up together, and we get 2 radical 2. Alrighty. Okay, so if we had negative third root of 6, or the cubed root of 6, plus 3 cubed roots of 6, again, we have the same index, same radicand. So we add or subtract the coefficients and leave the radical alone. This is going to give us negative 1 plus 3 is negative 2. Cubed roots of 6. So let's look at some of the problems. I didn't write down what problems these were, but you should be able to. Oh, no, these are still just more examples. Okay. So here we have 2 radical 5 plus 3 radical 20. Now, at first blush, you can look at these and go, hey, listen, they are not the same. Different radicand, even though they have the same index. So because they have different radicands, there's nothing doing. So, but we need to remember about reducing or simplifying radicals. So here we have the square root of 20. Now there are 2 ways you can do this. So 20 is not a perfect square. Your perfect squares are 1, 1 squared, 4, 2 squared, 9, 3 squared, and so on and so forth. So if you see something that you know is divisible by 4 or 9 or 16 or 25, it's fine to go ahead and pull that out. So here, we can do this as the square root of 4 times the square root of 5. And we know the square root of 4 is 2. So we have 2 radical 5. The other way to do it, especially in this, I'm doing it with 20, even though it probably works better with bigger numbers. You do the prime factorization of the number. So you write down, you just keep factoring out whatever you can until you're left with just prime numbers. So 20, what I like to do when I'm doing prime factorization is start off with 2. And once I get rid of all the 2s, then I go to 3s. Once I get rid of all the 3s, I go to 5s. Just take each little prime number out. So here we have 2. So that makes it 2 and 10. 10, I can pull out another 2. 2 and 5. 2 and 5 are both prime numbers. So now we have just all the prime numbers, 2, 2, and 5. Now, because this is a square root, because there's no index listed, we know the index is 2. So what we're looking for is sets of 2 of the same number. In this case, we have 2 2s, but I don't want to confuse you guys and say that it has to be 2s. That when, it's a square root, we can only pull 2s out. Here we're pulling a 2 out because we have 2 individual 2s. So because the index is 2, that means for every 2 inside we find, we can pull 1 out. And so then that gives us 2, and then we just write the square root of what's left over. So notice it doesn't really matter which way you do it, you're going to end up with 2 radical 5. So we go and we plug that back in. So now we have 2 radical 5 plus 3 times 2 radical 5, or 2 radical 5 plus 6 radical 5, which gives us 8 radical 5. I'm going to take a sip of coffee, be right back. Okay. Onward and upward. So, same general idea applies with the cubed root of 54. So here we're going to break it down. We're going to pull a 2 out. That goes 2 times 27. 27. Can't pull a 2 out. It's not even. But what about 3? Well, sure. I can pull 3 out. And it's 3 times 9. Hey, Cleo. Cleo really likes, the cubed root of 27, huh? Say hi. There you go. Okay. See? She said meow, which isn't really high. It's not even like high in cat because, well, it might be, but I don't speak cat. Did you know that wild cats don't meow? That meowing is something that cats developed in order to get the attention of humans. That they're meowing or purring. I forget. Anyway, again, it is now 11:40 at night. So 9 breaks down to 3 and 3. So here we have our prime factorization of 2, 3, 3, and 3. Now notice here that because the index is 3, we can't just take 2 3s, but we need 3 3s, or 3 4s, or 3 5s. We need the same number as the index. So if the index is 4, we need 4 to take out. And for every, so that index says for every 3 that you find, so here we have 3 3s, you can take 1 outside. Boom, boom, boom. There's a 3 there, 3 radical 2. And so that would be a simplification of the square root of 54. We had the 4th root of 48. That gives me 2 times 24, 2 times 12, 2 times 6, 2 times 3. So the prime factorization of 48 is 2 times 2 times 2 times 3. So notice here our index is 4. So we're looking for sets of 4. Here we have 4 2s, so we can pull 1 out. And we have 2 4th root of 3. I think we now go on to problems Oh, no, I'm going to explain why this works. So, and the other way to think about it is the cubed root of 27 equals 3, and that's because 3's cube is 27. They are inverse operations, the same way that addition and subtraction are inverse, and that multiplication and division are inverse. So the square root of 9 equals 3 because 3 squared equals 9. Okay, we now have, so this is, I believe, number 2. And I think I've done this in both my classes, but we'll do it again anyway. So we have negative cubed roots of negative 3. We have that minus 2 cubed roots of 3 minus 8. Now at first look, you're like, hey, we're all done. Even though they're all square roots, meaning they have the same index, none of them have the same base. But that doesn't mean we can't simplify. And sometimes when you simplify, common bases will show up. So here, we're going to start with the 8. So we have the square root of 8. 8 is 4 and 2. Now again, as I had done before, if I know that 4 is a perfect square, I can just rewrite this as 2 radical 2. Or, like so. Or I can break that 4 down to 2 times 2. And go, hey, it's a square root. So for every 2 2's I find, I can put 1 outside. And what's left? 2. Again, they're both the correct way to do this. But it just really depends on which way you find more valuable. So 2 third roots of 3. We have nothing doing. A bunch of prime numbers there. So now let's look here, and we have the third root of negative 3. So what I'm going to do here is I'm going to break that negative 3 into negative 1 times 3. So we can then break this down into the cubed root of negative 1 times the cubed root of 3. And what this does, 1's a special number when it comes to roots. Because if you have a positive 1, 1 to any power, or the nth root, or whatever number you put, the square root of 1 is 1, the fifth root of 1 is 1, the 10 billionth root of 1 is 1. So here we have negative 1. And now I know that if we multiply negative 1 times negative 1, we get positive 1. But then if we add in another negative 1, we get negative 1. And that's, for every odd power that I raise negative 1 to, I'm going to get negative 1. Negative 1 to the third is negative 1. Negative 1 to the fifth is negative 1. Negative 1 to the seventh is negative 1. And negative 1 to an even power, 2, 4, 6, and so on, is always going to be positive. So here I have the third root of negative 1. Well, that's just negative 1. So I have negative 1 times the third root of 3. And that gives me negative third roots of 3. Because I had 1 minus 2. Minus 2 radical 2. And that's my answer. Woo! I just gave it away. Now everyone knows the answer and no one's going to watch my videos. Oh, wait. No one watches my videos anyway. Actually, do you know who actually does watch my videos? Is former students. So if any former students are watching this just getting a laugh, then hi. So we have negative 2 fourth roots of 4 minus 3 fourth roots of 6 minus the fourth root of 324. Again, at first look, there's nothing doing here. We have the same radicans, or we have different radicans across the board, even though we have the same index. They're all fourth roots. So what I want to do is I want to kind of break apart that 324 to see if maybe I can rewrite it in a way that I would then be able to join it up with one of the other terms. There's no guarantee that this is going to happen, but in a problem, that's kind of what you're looking at. How do I simplify that big old number, the fourth root of 324, in order to make it match up with one of the other numbers. So we're just going to start breaking 324 down. 2 times 162. 262, we can pull out another 2. So 162 divided by 2 is 81. 81's not even, so I can't pull out any more 2's, but I can pull out a 3. 81 divided by 3 is 27, and as we already talked about, 27 breaks down into 3 different 3's. So that gives me this as the prime factorization of 324. 2 times 2 times 3 times 3 times 3 times 3. Now notice that we have a whole bunch of 3's there. Specifically, we have 4 3's. And because our index is 4, that means for every 4 3's we have underneath the radical sign, we can move 1 out. And what do we do with what's left over? Just multiply them together. So that's 2 times 2. That gives us 4. So the 4th root of 324 simplifies to 3 4th roots of 4. So now, look, we have negative 2 4th roots of 4 and 3 4th roots of 4. Negative 3 4th roots of 4. So here we have a issue where we have the exact same radicand, 4. We have the same index, 4. So we add or subtract them. And remember, when we're adding or subtracting, we add or subtract the coefficients, and we leave the radicands alone. So negative 2 minus 3 is negative 5. Square roots of 4, 4th roots of 4, minus 3 4th roots of 6. And that's our answer. Moving on, I wanted to do this one. So we have 2 radical 20 plus 3 radical 20 minus 3 radical 45. So before I start simplifying them, I want to do anything I can here. I see that I have 2 radical 20 plus 3 radical 20. I can join those together and get 5 radical 20 minus 3 radical 45. Now again, you're looking at this going, hey, I'm done. Neither 3 square roots of 45 nor 5 square roots of 20 have the same index. They do have the same index, but they don't have the same index and the same radicand. But that doesn't mean I can't simplify them. We've already done 20, and we know that 20 breaks down to 2 radical 5. If we look at 45, we know that 45, so we can't pull a 2 out, but I can pull a 5 out. That gives me 5 times 9. 9 is 3 times 3. And the square root of 3 is 3 radical 5. So if you're used to doing it the other way, that would have turned into 5 times 3 times 3. Here we have 2 3's, so we pull 1 3 out and get that. So let's rewrite this. So instead of 5 radical 20, we're at 5 times 2 radical 5 minus 3, and then instead of the square root of 45, I'm going to write 3 times the square root of 5. 5 times 2 is 10. 3 times 3 is 9. And then we have 10 radical 5 minus 9 radical 5, or the square root of 5. So I did this one, but I actually want to see what you guys can do with it. So try this out. If you can't get this, come in at lunch and I'll help you. So now we're on to the next set, and these are terms with both whole numbers as well as variables. And they're pretty straightforward. So here we have 112n squared, square root of. And so what we do is we look at this as the product, remember product means multiplication, of the square root of 112 times the square root of n squared. Now n squared simply breaks down to n times n, and hey, we know that if we have two of the same set, n and n, we can pull one out. Well, here there's nothing left when I pull them out. So we simply say that the square root of n squared is n. 112, we're going to pull off a 2. And that leaves us with 56. So we keep pulling off 2's until we can't anymore. And what are we left with? We're left with 4 2's and a 7. Now notice here, when we do the square root, we're looking for groups of 2. Well, we have 2 groups of 2's, of 2 2's, okay? So we have 4 total 2's there. 2 times 2 times 2 times 2 times 7. And so for every 2 2's I find, and it didn't matter whether they were 2's or 3's or 4's or 7's, for every 2 2's I find, I can pull 1 out. Here, I have 2 2's, so I can pull 2 out. So I have 2 times 2 times the square root of 7, or 4 radical 7. I then throw the n in there, and so my answer would be 4n times the square root of 7. So 80 b to the 4th, we have 80 times b to the 4th. Here, just like with those 2's, when we look here, we have 2 sets of b's. So we can pull out each one of those b's, and we get b squared. 80, factor it out. So we have the prime factorization of 80 being 2, 2, 2, 2, 2, 5. And because it's a square root for every set of 2 that we find, we can pull 1 out. We have 2 sets of 2, so I can pull 1 out. So that becomes 2 radical. Or 2 times 2 times the square root of 5, or 4 radical 5. So moving on. We need to add those 2 b's in. That's b squared, so we have 4b squared times the square root of 5. 98x. So we have the square root of 98 times the square root of x. 98 breaks down to 2 and 49. 49 is 7 and 7. So the prime factorization of 98 is 277. Here we have a set of 7's, so we can pull 1 out and end up with 7 radical 2. As to the square root of x, there's nothing doing. It doesn't have a partner, it doesn't have a pair, there's no way we can pull multiples of the same number under there. So we just leave it as the square root of x. And then we rewrite that as 2 times the square root, or 7 times the square root of 2x. Just going to go through some slides so you can kind of see the pattern. So, next up, multiplying. When we multiply radicals, all we need is the same index. They do not need to have the same radicand. So as long as they have the same index, then we multiply them. We multiply the coefficients, and we multiply the radicals. Leave the index alone. So for example, if we have the square root of 2 times the square root of 5, same index, 2. We multiply them together, and we get the square root of 10. So if we have 2 radical 2 times 4 radical 3, remember, we're going to multiply the coefficients together. That's 2 times 4, or 8. Then we multiply together the radicands. So 2 times 3 is 6. So here, again, I didn't write down what problem this was. But we have the third root of 3 times the third root of 5. Oh, I think this is just an example I give. So here, we leave the radical alone because, yeah, And so we have the third root of 15. And one of you guys also have problems requiring the use of the distribution property. So here we just take the same way we would with any other problem. We're going to take that negative 2 square roots of 5, and we're going to multiply it by everything inside the parentheses. So we have negative 2 square roots of 5 times negative square roots of 5 plus negative 2 square roots of 5 times 2. We then do both sets of multiplication. So on the left-hand side, we have negative 2 radical 5 times the negative square root of 5. So you just multiply those through. Apparently, I kind of zoned out. So that gives us 2 times the square root of 25 plus negative 4 roots of 5. The square root of 25 is just 5, so that turns into 2 times 5 minus 4 radical 5. 5 times 2 is 10. And that would be our answer. If we have a problem like this, we're simply going to FOIL it. Like full-on FOIL, first, outer, inner, last. So for the first ones, we have 5 radical 2 times 5 radical 2. We then complete it out. 5 times 5 is 25. The square root of 2 times the square root of 2 is 4. 5 times 1 is 5. 2 times 3 is 6. So again, what we're looking at is multiplying the coefficients by each other, and then the radicands by each other. We leave the index alone. So then we have negative 3 radical 3 plus 5 radical 2. Negative 3 times 5 is negative 15. And 3 times 2 is 6. And then we end up with negative 3 times the square root of 9, because we multiply our radicands and we multiply our coefficients. So the square root of 4 is 2. So we have 25 times 2. The 5 radical 6 and the negative 15 radical 6 we can set up as a different bank. And then we have the square root of 3, so the square root of 9 over 3. That turns into negative 3 times 3. 25 times 2 is 50. 3 times 3 is 9. Combine those and we get 41 minus 10 radical 6. Hopefully this helped. If you have any questions, please let me know.